And so I'm Isaac Smith. I'm the other co-lead after Paul and Shane, and it's a distinct pleasure to introduce Pat Becerra. Pat is coming to us from the Physikalisches Institut Bern. He works with Nick Thomas there. He's at the University of Bern. So he did his PhD at the University of Arizona, working with Shane here. And he's done a high-resolution observational study of the Martian polar regions and their connection to climate, which is exactly the topic. So he's the world expert on this exact thing that we're doing.
Wow.
And so it's a great pleasure to have him. Formerly, he did his master's degree at the University of Arizona, and he did his BS at the Pontificia Universidad Católica del Perú. So that's where was it physics or was it?
It was physics, yes.
Okay. And then he's also had an NESSF, which is a distinguished NASA fellowship. Okay, thanks.
Thanks for that introduction, Isaac. See if I can live up to it. Okay, so well, thanks for having me, and thanks to the organizers for organizing this workshop. I'm really excited for the next week. So during this talk, I'm going to be talking about some techniques and methods that we use to measure, to observe the stratigraphy of the polar layer deposits and to measure these periodicities that Shane has mentioned in his talk. So the answer to this question, why study the stratigraphy, should be pretty apparent from Shane's talk already. But just to kind of put it in the framework of the Mars Polar Science meeting that we had last year in Iceland, which kind of drives the development of our subfield. These are two of the 5 main questions that we came out of the meeting, or that came out rather of the meeting. Essentially, what we're saying is, you can read the questions there, but what can we learn about the climate from looking and studying at the layers themselves, at the patterns in the layers themselves? And so, in order to answer these questions, we need to study the stratigraphy. We need a detailed knowledge of the properties and how they're arranged in the record. And we need a way to be able to correlate them to Mars's climate history, which is influenced by the evolution of the astronomical parameters, as you saw in Shane's talk. And so our goals are then to determine the age of specific layers and what the climate state was when they were deposited. And so that'll give us a detailed understanding of the geologically recent history of the Martian environment. Okay, so in order to do this, we need the most accurate characterization of the internal layering that we can get. And so this is very important. And in order to do this, the stratigraphic properties that we want to measure need to be those that are most closely related to the environments in which the layers were deposited. So for example, dust to ice ratio, different isotope variations, etc. Since we don't have in situ sampling yet, then we primarily have 2 choices. We have imaging and we have radar, and Shane's talked about both of these. And these are again topographic maps of both poles. These are CTX images that are about 6 meters per pixel, and you can see where they are in the pole here. And these are what the layers look like in high rise. You've seen that as well in Shane's talk. So from this data, we can get, we're basically looking at the outcrops. So the information from the layers is actually information about the outcrop. So we're getting brightness at the outcrop, morphology, slope, topographic expression, all at the outcrop. And so the relationship between the properties of the layers at the outcrop and the internal layers is very complex. With radar, as you saw, we can see the internal structure of the layers. We can view the deepest layers as well. And so this is really great. This is it's a huge advance to our science. But the relationship between these reflectors and the outcrops is kind of unclear, as Shane also made the point in his talk. Okay, so I'm going to talk about some of the methods that we use to map the stratigraphy of the poles. So first, we want to get kind of a geologic framework in which we're looking at these fine resolution stratigraphic columns. And so these are geologic maps that were made by Ken Tanaka's group at the USGS. And the way that these are built is essentially we look at the widespread image coverage throughout both caps and the topography, and we visually identify broad stratigraphic units and unconformities, and we can get ages from crater statistics. And so this is kind of just the larger scale geologic map of the area. And as far as the polar layered deposits themselves, in the SPLD, we're going to be looking at these units here from AA1 all the way up to AA4b, which is the South Polar Residual Cap that Shane showed detailed pictures of with the nice pits and everything. And in the North Pole, we're looking at these 3 units. So these 2 are the basal unit that Shane discussed, and these 3 are the polar layer deposits themselves. This is the North Polar Residual Cap. Okay, so if we want to get at patterns in the layers and at how they're correlated to the orbital history, we have to look at the stratigraphic column in a little bit more detail. And so the first, intuitively, the first thing we want to do is try to correlate different sequences of layers. So in order to do this, we look at images throughout the cap, and we try to correlate, like I said, sequences of layers. Because of the periodic nature of the layers and of the exposures, correlating one layer by its morphology to a similar layer at another site is pretty unreliable. You can get layers that look the same that are not exactly the same bed. So that's why you do sequences that are in the same order, and you try to find them in other locations. So this is an example from Fishman and Wittberg in 2006 using mock images, and this is from Milkovich and Plaut in the South Pole, and you can see that the analysis is the same. However, like I said, because of the periodic nature of the PLD, this can also be, can have some uncertainty as well. You can also have full sequences that can look the same throughout different areas of the cap. And so what we want to try and do is look at, first of all, the highest resolution images that we can, now that we have them available, and then also try to do some different type of feature comparison between the sites. So with high resolution stereo, that allows a variety of different measurements that we didn't have before. So here we have a high-rise DTM, or digital terrain model, and from that we can get a number of different quantities. For example, you can get an elevation profile, which you see here, and then from that you can get the topographic expression of the layers at varying wavelengths. So what I mean here is you can basically kind of measure how much the topography kind of deviates from a local linear fit to the scarp, and that'll give you a continuous profile like this of this layer topographic expression or protrusion versus depth. If you take just the first derivative of this elevation profile, you can get instantaneous or local slope. And then from the orthorectified image that you can get as a byproduct of making the digital terrain model, you can observe continuous profiles of map view brightness. So the importance of having these continuous profiles is not only that you can use different techniques to analyze the similarities, but also that you can do signal analysis on them, and then you can compare to the same sort of signal analysis that you do on the periodic functions that should drive these deposits. So as far as the correlation and the signal matching, we can use different techniques to match these profiles. One of these techniques is called dynamic time warping, which I've used in some of my work. And what this algorithm does, this was actually developed for voice recognition. And what it does is it basically takes a pair of signals that have similarities. And this is just the same protrusion signal that I showed before. You have 2 signals here, and this will be depth here, and this is protrusion. This was taken from these 2 sites. And so the algorithm takes these 2 signals that have similar features, but that their similarities are not so apparent because of the difference in each feature, the difference in depth range or time range of each feature. And it warps the time or the depth dimension so that the similarities between the signals are more apparent. And not only that, it gives you a parameter that measures how good this correlation is. The more you have to warp the signals in order for them to match, the worse your match is, the worse your correlation is. So this is one of the techniques we use, and what's nice about this is, even though in the end, it's doing the same thing that we are doing by eye. This is something that's repeatable, it's measurable, and we can use it. We can do it for a large number of images. Okay, so that's the signal matching techniques, and then I'm going to talk a little bit about the radar, and I'll go back to the time series analysis in a little bit. So Shane also kind of covered this already. This is from Pudzik et al. 2009, and so we can see the internal structure with the radar. You already know that. The radar is expressed. The radar data is shown in these radargrams, which are basically images where you have distance along track here and delay time, and then the power is the image itself. Now, the delay time is directly related to the depth, and you have to convert it in this way, shown in this equation here, where you have depth, time delay, the speed of light, and this is the permittivity that of the medium that you're going through, which was estimated actually from Sherrod and Mola for the NPLD to be around 3.15. And as Shane mentioned, this was one of the big discoveries using radar, was that we could see all the way to the bottom of the polar layer deposits, and that gave us an idea that this was relatively pure ice. So when you have good Sherrod coverage like this, then you can correlate each of these reflectors to each of these reflection zones to each other, and then you can kind of make paleosurfaces, which Shane also showed in his talk. And so essentially what you have here is a radar-based stratigraphy that is distinct from the stratigraphy that you're building with the trough exposures. Okay, so what we want to do, as I mentioned before, this is all driven by the connection of the PLD to climate. That's our main goal. And so in order to search for these periodicities in the data, and if they correlate to the variation in orbital parameters, we use techniques known as time series analysis or spectral analysis. And they're basically techniques that decompose functions into their periodic components. So the most famous of that is fast Fourier transform. And there's another technique also called wavelet analysis, which has a variety of uses, but you can also use it to decompose periodic functions and kind of get at what the periodic components are. So just as an example, this is the installation function that Shane also showed in his talk, and you have it here all the way to 5 million years, and you can see the different cyclic variations. And when you take the Fourier transform of that, you can see that the two main peaks correspond to a 51,000-year period of the precession of the orbit that Shane mentioned, and then you have this peak that corresponds to the first obliquity oscillation period, 120,000 years. So at this timescale, these are the two most important peaks that drive this function. As far as wavelet analysis, the advantage of using that to analyze these signals is that you can not only see the dominant frequencies, the dominant periodicities of the signal, you can also see how these vary with depth. So instead of having this is the same thing that I showed before, instead of having just radar power versus wavelength or periodicity, you have here periodicity and then time, and then you have power in the z-axis, so you have it in color where red is higher. And so you can again see this band here being the obliquity oscillation period, and this being the argument of perihelion precession period. Okay, so now I'm going to summarize some of the results and the progress that's been made in this field in the past few years. And I'll start with the SPLD, that, as you probably got the idea from Shane's talk as well, has been not as studied as the North Pole layer deposits have. They're much more complicated. They're much more, they're covered in this dust lag. They're a little bit harder to explore. They're much older. And so that all influences how and why these studies are done. And so going off of Ken Tanaka's geologic map, Milkovich and Plout in 2008, they visibly correlated sequences using the technique that I showed before by their morphology in Themis images, which had greater coverage at the time than, for example, now we would probably use something like CTX. And they identified 3 large-scale sequences of layers, 2 of which they observed directly and 1 of which they inferred. So the first one is the Promethae-Lingula layer sequence, so-called because there are really nice exposures in this area of Promethae-Lingula and this this area here called ultimi lobe. And that sequence itself is divided into 4 subsequences of between 100 to 350 meters each. And they're morphologically divided, and which is, is pretty apparent from the image here. And they correlated this sequence throughout all of these locations on the South Polar layer deposits. And the background is molar topography, by the way. The next sequence is the bench forming layer sequence, which was identified by Shane and Anton Ivanov in 2004, and using MOLA, Themis, and mock data. And Milkovich and Ploud then found the same image and correlated it through these sections here. And this sequence is identified by these bench-forming layers. You can clearly see them here, this sort of stair-step morphology and kind of hummocky, knobby layers that identify the sequence. This same paper attempted a correlation between these 2 units by possibly identifying a bench-forming layer in a location where they had possibly identified the same PLL. Now, this wasn't definitive, but they concluded that the BFL was basically on top of the PLL. And so this is their like kind of broad stratigraphy that they came up with, where you have the PLL sequence covering all of the area of this SPLD, and then you have the BFL constrained to this area. And then they had an inferred layer sequence, which they inferred the existence of by looking at exposures of the PLL around the Prometheus lingula area, and the bottom of that represented actually the contact with the substrate, whereas in the exposures around this part of the cap, the PLL was at much, much higher elevation and appeared to have, just from the MOLA interpolation of the surrounding surface, appeared to have a lot of material underneath. And so they inferred that there must be another sequence under that. As far as periodicity analysis, really one of the only works that's been done on this was by Lemay et al. In 2012. And they measured the thickness of layers using high-rise DTMs at 3 locations on the SPLD. And you can see those here. And what they found is a high variability in bed thickness. You can see here, this is just number versus the bed thickness that they measured. And they also did some spectral analysis. They had the DTM so they could make continuous profiles of slope, continuous profiles of brightness as well. And they actually did not find any statistically significant or consistent stratigraphic wavelength detected. This is the Fourier transform, and you can see wavelength here on top. This is the raw spectrum, and these are statistically significant levels, which I don't have time to get into that right now. But basically, if you will have a peak over these statistically significant contours, then you can consider it significant. As far as results from radar, as Shane already mentioned, we mostly used MARSIS to measure the bottom of the South Polar layer deposits. So Ploud et al. In 2007 used MARSIS to measure the thickness of the SPLD. They mapped the base using a dielectric constant of 3, assuming water ice. And then they mapped the surface throughout the whole extent of the polar layer deposits, and you can see that here. And then basically calculated the difference between this surface and the MOLA topography to calculate the thickness of the South Polar layer deposits, which they found to be at most 3.5 kilometers in this area here on the SPRC. Milkovich et al. In 2009 did a very in-depth analysis of the area in Prometheus lingula here, where you can see the layers in Charade. And Shane showed the same image to showcase the fact that you can see the reflectors. But what's interesting about what they did here is that they could see these packets of 8 to 10 reflectors that were bounded by these zones of lower reflections. And in the MARSIS data, they actually saw 3 subsurface reflectors that they were able to map to these darker layers in Charade. So that means that there's a high contrast in permittivity that's causing these reflectors in both data sets. And furthermore, they took this was the first study that took that kind of first step to try and correlate radar reflectors to visible images by trying to tie these MARSIS reflectors to groups of layers in Themis. they basically measured the elevations of these Mars's reflectors and compared them to the elevations of prominent layers in Themis, and found that these reflectors did roughly correlate to some of these layers. And so that was evidence of a relationship between the radar reflectors and the exposed layers in the SPLD. And so this could be dust to ice ratio, this could be a number of different things, but at least we know that the radargrams do appear to mimic the exposed layers. Okay, and again, I think Shane showed this as well, and so I'm going to go into a little bit more detail about this discovery of the CO2 ice unit. So this unit that was discovered by Phillips et al. 2011, and it was further characterized by Bierson et al. Last year, and this was the same radargram that Shane showed. They basically found large deposits of buried CO2 ice, and you can see the thickness and the extent of those deposits here. This is the South Polar residual cap. That's the South Pole right there. And so this unit, they inferred that it corresponded to the AA3 unit of Tanaka et al. 2007. The Bierson et al. Further characterized the unit that was first detected by Phillips et al., and they were the ones that found these reflectors that Shane was just discussing. He also mentioned that there's enough CO2 ice there to double Mars's atmospheric pressure. But this cartoon basically comes from a model that they did, and the model showed essentially two things. One, that CO2 ice can actually accumulate during low obliquity. You can see this is results from their thermal model. And you can see that CO2 ice is able to appear at these locations. This is CO2 versus time here. And the second thing that they showed is that when you have these bounding layers, which are the water ice layers, when you have them be as thick as they had found them to be in the radar, it is able to sequester and kind of protect the CO2 from sublimation. They didn't find how these bounding layers were formed to begin with, but they found that this scenario can exist. And so they subdivided this AA3 unit into 3 CO2 units and 3 water ice bounding layers. So with this, we can now get kind of an up-to-date picture of the gross SPLD stratigraphy. And so this is Tanaka's geologic map. Again, we're looking at these units here, and so we have AA1 and AA2, and that roughly corresponds to the BFL and the PLL. Now, I'm not entirely, I'm just totally speculating here. There hasn't been like detailed work done on this correlation. But roughly they should correspond to that. And then we know that AA3 corresponds to that CO2 unit, which is shown by this modeling, which was shown to be about 340,000 years old at most. And then you have the SPRC on top with the CO2 unit and the bottom water ice unit. Okay, so now on to the PLD. So as opposed to the SPLD, the North Polar layer deposits, the study of their stratigraphy with images was kind of driven a lot by the signal analysis. So I'm kind of going to tell a story of how this happened and how this research was done. So the first of these was Lasker et al. In 2002 compared a 350-meter profile of Mach brightness to the installation history. And you can see the Mach image here. And here you have the brightness profile that he's kind of overplotted over the installation, kind of to compare peaks. And this is the Fourier transform here, where you have frequency and power here, and you have he's basically comparing these two peaks. And so the main conclusion from this first study was that this 350-meter section was driven by the 51,000-year argument of perihelion period, which, if you have this depth, would correspond to an accumulation rate of about 0.5 millimeters per year. Next, Milkovich and Head in 2005 found a 30-meter wavelength in the upper 300 meters, which you can see there. So here's 30 meters right there. This is the brightness profile, again, of Mach images. They did a very in-depth study, looked at a lot of Mach images, and found this 30-meter wavelength to be common in a bunch of these images. This is just basically a composite of a bunch of their Mach images. And so they kind of confirmed this observation that the top 300 meters was driven by this periodicity and had an accumulation rate of about 0.5 millimeters per year. However, in 2009, Taylor Perron and Peter Hybers did a wavelet analysis study on these mock images, and they actually didn't find this 30-meter periodicity, at least not to any statistical significance. But they did find a short wavelength periodicity at 1.6 meters. This is the wavelet spectrum here, and this is an example. This is an example analysis that they did. This is the mock image here, depth, wavelength here, and power. These are power contours. You can't see them very well, but the important part here is that these pink areas are that power that they found that rises over their statistical significance background. And so at this point, it started becoming apparent that it wasn't so easy, it wasn't so straightforward as it had seemed before to tie the periodicities in the polar layer deposits to the orbital history. However, we have to remember that we're looking at these outcrops, and so this brightness that we're looking at is affected by a bunch of different things, including that sublimation lag that Shane talked about during his talk. And in addition to this, without an absolute chronology, without a date to a layer, we can't really tie a specific periodicity to a specific layer pattern, because that could be repeated at depth. You know, it's a lot more complicated than this. So there, after this, there are a few steps that we were able to take. After the mock images, with MRO, we got high-resolution images with high-rise, and we had stereo, and that allowed layer-scale topographic measurements. And so in 2010, Fishbaugh et al. Built the first stratigraphic column at the layer scale, at the scale of the layers, which you can see here. And this is a high-rise image of the area. And basically, they divided the beds into marker beds, which are these darker, sort of hummocky type layers that you can see here, and thin layer sets, which are sets of thin, erosionally resistant layers. And so they postulated that they had found both periodicities, that they had found in the marker bed spacing, they had found the 30-meter periodicity that Lescar et al. Found, that Milkovich and Head found, and that they had also found the 1.6 meter periodicity of Perron and Hybers in the periodicity of the thin layers within the sets. And then the same Lemay et al. Study that I mentioned before that studied the SPLD also did a study in the NPLD, and they found that the thicknesses of these layers were clustered more around these lower values. And with spectral analysis, they also found the only statistically significant periodicity to be 1.6 meters with thickness measurements and fast Fourier transform of both slope and brightness. So not only did they observe and confirm the Perron and Hybers periodicity, but they also observed a relationship between the thickness measurements and the brightness patterns, indicating that the brightness patterns are actually giving you some information. They're not completely unrelated to the internal. They're not just the sublimation lag that you're measuring. And so later on, in a paper that we published last year, we looked at layer protrusion at this site and a number of other sites by increasing the high-rise DTM coverage, and we were able to correlate the topographic expression of the layers to these layers in the Fishbaugh et al. Column, as you can see here. And not only that, but the main point of our work was really to try and correlate these sites, a number of these sites to each other. And so for that, we used we tried to trace the layers within CTX images along the same troughs, and then we also used the dynamic time warping that I explained earlier in order to try to correlate these sites to each other. And so this is an example of what that looks like. These are the two high-rise images and how the resulting correlation would look like. And here you have one protrusion profile of this N0 site here, which is the same site where this is why it's in yellow, because this is the site where the Fishbaugh et al. Column was built. And then you have this other site here, N1, which is over here, And you can see that there's a pretty good match over here where you have both layers, both profiles kind of overlain. The only thing you have to know about this middle section is that this path shows the way in which the signals had to be modified in order for them to match. And so this is a fairly statistically good match. And so we did that for a number of sites, and we were able to correlate 5 sites to N0. And so these 5 sites, or these 6 sites, if you include N0, are shown here, and that covers about 7% of the area of the NPLD, and it includes the sequence of layers that was measured by Fischbau et al. In 2010, and that we call the main sequence, and that we basically conclude that that sequence probably is valid at that resolution for at least this area of the cap. Okay, so as far as wavelet analysis, as far as signal analysis of this high resolution imaging, some of the latest results we presented, we published in a paper earlier this year, and we tried to get at the problem of the lack of absolute chronology by looking at, instead of looking at one wavelength and trying to compare that to one periodicity, we wanted to look at ratios of wavelengths that can be more diagnostic of the known installation periodicities. And so, kind of running short on time here, so I'm going to kind of try and go quickly through this. But basically, this is the installation signal through time. And so this is the same kind of wavelet spectrum that I showed before. This is the 120,000 year periodicity, and this is the 51,000 year. And they have a ratio of 2.35. When we looked at data from all 16 of these sites, we looked at protrusion, we looked at slope, we looked at brightness, and the mean ratio of the periodicities of all of these, of the statistically significant periodicities that we found in all the data was 1.98. And so this is lower than this ratio. However, when we used a thermal model that had been published by Widberg et al. In 2012, and this is a model of accumulation based on just a thermal energy balance model that builds up the cap, and you have this column of dust fraction versus depth. And when we looked at the periodicities present in that simulated stratigraphy, the ratios ended up being very similar to what we had found in the data. So this indicates that this model is at least on the right track. Granted, this model is constrained by that by that Fischbau and et al. Stratigraphic column, but it indicates that we're kind of on the right track. Okay, and so as far as radar, I'm going to go quickly through this because Shane already went through it. So this is the same plot that he showed from Putzig et al. And so these are the 5 units that they identified. You have packet zones and interpacket zones where you have a lot of reflectors, and then you have more tenuous reflectors in these areas here. And those were correlated to correspond to these different portions of the insolation history of Mars, where you have interpacket areas corresponding to low amplitude insolation oscillation, and then packet, where you have the packet areas correspond to these higher amplitude areas. And so that means that the packet reflectors are then driven by dust content changes during periods where ice is actually accumulating. Okay, Shane kind of really already showed this as well. Isaac published a paper last year showing this most recent, that the most recent accumulation has sped up, and this is shown in by the extent of this unconformity here to the widespread recent accumulation package, which is basically this top group of layers and reflectors here. And so just to finish up, there's the future direction that we want to go to is basically to try and correlate these two stratigraphies. You might have noticed that both the radar and the visible stratigraphy are kind of studied on their own. And this is, the problems that we're having now is kind of reminiscent of terrestrial climate issues, science issues, where you had Milankovitch cycles ultimately confirmed by the correlation of a number of different data sets. And so the goal is to combine and correlate this optical data to the radar data to inform our modeling. So Christian et al. In 2013 was the first to do this quantitatively, and they found a correlation between the long wavelength shape and also similar wavelengths as far as the Fourier transform goes for these radar profiles as the Milkovich and Head 2005 paper. And so there's a general agreement between a number of these characteristics in the radar and the visible, but one-to-one layer packet correlation is not possible yet. And then this year, Dan Lalich, who is here, published a paper where they basically tested the hypothesis that reflectors are caused by these marker beds, which I've mentioned before. And what they found is that basically the correlation between reflectors and modeled marker beds, so these are modeled marker beds with the same model that I used for my wavelet analysis based on Wittberg et al. 2012. And so these are high protrusion beds or marker beds, and they appear to correlate well with these marker beds that Lalich et al. Looked at in the radar. And so just to wrap up, some of the future stuff that we want to do, and this is something that I've started to work on recently, is basically bring all of this together. Use the high-rise topography to inform a radar propagation model, and so that we have a simulated radar which we can compare to a real radargram using the signal matching and spectral techniques that I've discussed. And so we're going to see what comes out of that. This is kind of a first attempt at that. And then finally, the overall kind of goal here of these stratigraphic studies and these signal searches is basically to obtain a dust-to-ice ratio stratigraphic column that describes the whole cap so that we can input that into orbital-based accumulation models, and we can get a complete picture of the climate history. In the future, of course, and this is, I guess, something we're going to be discussing, I hope, at this workshop, samples would be ideal. We can get a lot more detailed measurements. And another thing that we should really start to do is to improve analysis on the SPLD so that we can kind of build a comparative history of both regions. And so I'll leave it at that. Thanks.